Okay, all right, let's look at C. If light with a wavelength of 456 nanometers is shone on the surface, what will be the maximum kinetic energy of the ejected photoelectrons? So the very first thing you have to do is find the energy of the photon. And of course, we use Planck's law for that. Okay, that's pretty straightforward. Energy is going to be hc divided by lambda, or h times f, depending on what we have. In this case, we have lambda. So again, 6.63 times 10 to the negative 34, 3 times 10 to the 8, sweet, divided all by our wavelength, which is 456, times 10 to the negative 9 to make it meters. All good there? Any questions for me? All right, what are we getting for the energy of the photon? Megan has 4.36 times 10 to the negative 19 joules. Killing it. Okay, 4.36 times 10 to the negative 19 joules. Awesome. 10 to the negative 19 joules is a pretty standard range because remember, we're quantum, we're itty bitty. Step 2, we are going to use the photo effect. 2. Use photo effect. Okay, in order to do that, we are going to write out the photo effect equation. And we want to know the maximum kinetic energy. So the last variable is our mystery here. Our E photon we just calculated. It is 4.36 times 10 to the negative 19 joules. The work function we calculated previously. So if we look back up here for just a second, our work function is 3.68 times 10 to the negative 19. Remember, we're still on the same question. There's 4 parts to it. It's long. 3.68 times 10 to the negative 19 joules, and we want EK max. Well, now we're going to do what? How do we solve for EK max? This is algebra. How do I solve for EK max? Oh boy, oh boy. No takers. We are going to use subtraction, my darlings. Holy Toledo Batman. We need to subtract 3.68 times 10 to the negative 19 from each side of our equation. Noah's gone ahead and done it. 3.68 times 10 to the negative 19. Beautiful. So this means that EK max is going to be 0.68 times 10 to the negative 19 joules. And that's a really weird way of writing something. So generally we'll try to put it in scientific notation. I'm looking at the question. I see that I require 3 sig figs. So I'm going to write it like this. 6.80 times 10, what will it be? Negative 18 or negative 20? Well, it now needs to move one more place left. So it's going to be negative 20 joules. Okay, all right. So as you're probably gathering, these questions take practice. And there's a lot of different ways they can be worded and set up. So the more practice you do, the more likely you are to succeed on your assessments. But that's not new. What stopping potential would be measured in the case of C? So last day we looked at the stopping potential, which was EK max is equal to E times V stop. Perfect. We know EK max, it is 6.80 times 10 to the negative 20 joules is equal to 1.60 times 10 to the negative 19 joules times V stop. When we divide V stop is going to equal 0.425 volts. Haha, there it is. Any questions about that one? Good. Love to hear good. Anyone else? Good, bad, or indifferent? Are we dividing this time when we subtracted the last time? Oh, buddy. Yes. Over here, we have E times V. In the previous one, we had 3.68 times 10 to the negative 19 plus EK max. Always do the opposite of what the operation is. The photoelectric effect graph. You see along the x-axis, we have frequency. That frequency is for one photon. Along the y-axis, we have kinetic energy for one emitted electron. Interesting. Okay, now here's the very snazzy part. The slope of each of these lines, if you notice, they are parallel, right? We've got 2 parallel lines here. So will the slopes be the same or different? by same. Okay, so the slope is going to give us something that is constant. Oh, good. Which is Planck's constant. And that is the same on either line. And in fact, any line where we have a true photoelectric effect graph. So they would be the same, absolutely. If they're parallel, they've got to have the same slope. How about the x-intercept? Any guesses about what that could tell us? So like right here, knowing that on the y-axis, we have kinetic energy. On the x-axis, we have the frequency of one photon. Watch the rest of the recording. See you. The x-intercept is the threshold frequency. Otherwise known as F naught, and that is the lowest frequency at which the photo effect would occur. Now, the even schnazzier part. If we extend these lines such that they cross the y-axis, and we get their y-intercept. This one might even go off the graph, and that is okay. There we go. That, believe it or not, is the work function. So y-intercept should put a dot there and label it maybe over here instead. Y-intercept is so this will be important in both your lab as well as in your assessments. Now, this is an okay resource, but there's also a photoelectric effect graph in Brightspace for you. And I have put a little note down here to read the textbook if you're being challenged by the concepts. So there's the photoelectric effect graph, but I'm also going to show it to you in Brightspace so you know exactly where to access it. So if we go into content, all the way down to Unit 4, there is a little spot, and I'm making it visible right now. It is the photoelectric effect graphs. So sharing that screen, here's what we have. And there's some really nice notes about the photoelectric effect graphs that are great to reference. So vertical axis is energy, horizontal is frequency. If we find the slope, you get Planck's constant. The threshold frequency is where the graph crosses the x-axis. The work function is where it crosses the y-axis. So it's very, very, very much worth reading these 3 pages because this is going to be a very common question that we're going to look at in the next couple of days.